all, I would like to thank you very much accepting our invitation to give a talk today. So I will start with a short introduction, and then I'll leave the stage for you for your presentation. So Professor Yu is currently an assistant professor at the Department of Computer Science and Engineering at the University of California, San Diego. She received her PhD from University of Southern California in 2017, and before joining UCSD in 2020, she has been a postdoc scholar at Caltech and also an assistant professor at Northeastern University. She has received multiple awards, among others, Faculty Research Award from Facebook, Google, Amazon, Adobe, several Best Paper Awards, Best Dissertation Award at University of Southern California, and also nominated as one of the MIT Rising Stars in electrical engineering and computer science. And her research focuses on advancing machine learning techniques for large-scale spatiotemporal data analysis with application on sustainability, health, and physical science. Thank you very much, Professor Yu. Stage is yours.
Thank you. Can you enable screen sharing?
Oh, yes.
Right. Can you see the slides? Good. Okay. Hi,
Yes.
everybody. Thanks for the invitation. It's a great pleasure to be here and give a talk remotely. So I am assistant professor at the computer science department at UC San Diego, and I direct the spatial-temporal machine learning lab. So this is the logo of our lab, and you can see here there is a rose in this logo. And there's also a hidden letter, S and T, stands for spatial-temporal. So that's the mission of our lab. Let me give you a few examples of what I mean by learning spatial-temporal dynamics. So this video is the progression of the pandemic in the past few weeks. And this is also the reason I cannot visit you guys in person, even though I really want to. So pandemic is only increasing in frequency, magnitude, and complexity, leading to difficult environmental and societal consequences. So forecast of death and hospitalization and cases would help inform public health decision-making. The problem is that simulating this type of complex interactions in spatial-temporal regime to model the progression of disease is very computation expensive. On top of that, the data collected in the real world is very noisy, often contain missing data. So the question is, how can we design appropriate machine learning methods that can speed up the simulation for dynamic progression and build more accurate models? Example is in the world of climate science. So we all know climate models are important tools for improving our understanding and predictivity of climate behavior. Unfortunately, climate models are very difficult to simulate at high resolution. They're often limited by a numerical integration from first principle modeling. This video shows the past temperature variation for the past 50 years, collected by several thousands of weather stations. The question is, can we combine simulation data with this observational data and build faster and more accurate climate models to help our climate scientists? The third example is in the world of transportation. So again, in the transportation research, traditional methods rely on strong model assumptions to simulate drivers' behavior. At the same time, these models are quite rigid and not consistent with real-world traffic patterns. This video shows the traffic flow in LA, the city of LA, from morning to night, and the bubbles represent the accidents happening at different places in LA. So again, the question is, can we combine this type of real-time sensor data collected at high frequency with better machine learning models to better describe traffic patterns and improve our trajectory planning and traffic control. So as you can see now from these three examples, there is a shared pattern among these domains, from public health to climate science to transportation and many other fields in science and engineering. The data that is generated in these domains is very different from the traditional machine learning applications, such as images in computer vision or text data in natural language processing. The data that is generated from this field contains very rich space and time information. And if we can learn from this such spatial and temporal data and learn the accurate dynamics, it will help us extract new novel insights about this type of domains and make progress towards real-time decision-making in science and engineering problems. And that's basically the focus of our lab. In the past few years, we have been developing a paradigm called physics-guided AI learning, because we think this type of spatial temporal data is often generated by certain physical systems. And therefore, it's important to consider the underlying physics of this kind of system. So physics as a discipline has always been used to study the pattern of space-time data, and it used first principle methods and build model-based approaches to describe space and time patterns. In physics, we have a lot of tools such as tensor network, which is what I did my PhD on, differential equations, and symmetries. So physics-based method encode our domain knowledge. Therefore, it's very sample efficient, meaning that they can learn with very few data points. Unfortunately, physics-based methods are computationally expensive. Sometimes because of numerical integration, we have to make approximations of the underlying equation, and that lead to model misspecification problem, which means this physics-based first principle methods cannot describe the complexity of real-world data. On the other hand, we have machine learning, which is a statistical inference approach. So we build data-driven methods to describe complex data patterns. So in machine learning, we also have our own tools, such as graphical models, neural networks, or deep learning, and variational Bayes, which is type of approximate Bayesian inference techniques. So machine learning methods are computationally efficient. They can learn from real-world data with minimum assumptions. So they're quite flexible and can lead to realistic models. However, machine learning models are learning from data. Therefore, it needs a lot of data to learn. So they're not quite sample efficient. In certain engineering domains, collecting data is very expensive. So that's a limitation of some machine learning-based methods. Most importantly, I would also want to argue that when we apply data-driven methods to science and engineering problems, sometimes the predictions are not guaranteed to be physically meaningful or scientifically valid. So we need to design hybrid method that can guarantee the physical consistency of the predictions such that we can encode inductive biases as our domain knowledge and improve generalization of these methods to on-scene data and on-scene scenarios, reduce sample complexity of the learning, and most importantly, to increase our trust in this new generation of AI methods. And that's the essence of this hybrid paradigm called physics-guided learning. So in this today's talk, I will focus on a particular aspect of physics-guided learning, which is how can we integrate physical principles to improve the generalization of existing deep learning models for learning complex spatial temporal dynamics. Before that, any questions? Okay, so let me continue. So there is a fundamental challenge with learning dynamics. Here's a very toy example of learning dynamics problem. And this is an example we showed in our paper at L4DC this year. Essentially, we're looking at the forecasting problem. So we're learning the dynamics of simple sine functions. In this case, we have a sine curve. On the vertical line in the middle, you can see that there is a sine curve. These are the past states we feed into the neural network as input. And then the future states on the right-hand side of this vertical line is the target predictions. So the dynamics of the sine function is very simple. It's governed by the phase parameter and the initial and the frequency. So we call these two parameters parameter theta, just for simplicity. So you can see that the training, so in experiments, we will draw samples from a certain interval of theta, meaning that we will select interval A and B, and then we randomly sample different parameters of theta and generate the corresponding sine curves. And in the testing, we will do the same, where we sample some of the dynamics from interval A and B, and then generate the corresponding testing examples. We made sure that the training samples and the testing samples are not overlapping with each other. So in this case, what you can see is that when we feed a deep learning model, this is a sequence-to-sequence model, is a deep learning dynamics learning model. It takes the past states as an input, encode that into hidden states, and then generate the future states as forecast. It's not surprising that the predictions from the seq-to-seq model can perfectly fit the target states. So this is in the interpolation region, and the deep learning models work perfectly. However, when we slightly change the experimental settings, where in the training, we will sample the parameters of the sine curve from the interval A and B, in the testing, we will sample the parameters of the sine curve from the different intervals, B and C. So now we're in the extrapolation region of the dynamics. We can see that no matter how powerful the deep learning model is, it cannot learn the correct states during the forecasting phase. So the model always have a bias from the ground truth data in a solid line. And with various deep learning models, none of them can work in this extrapolation regime. So this points us to one of the fundamental challenges in dynamics learning, which is distributional shift. So we know that deep learning struggles with changing dynamics. The machine learning, we call this distribution shift or covariance shift problem. I also want to note that this type of covariance shift problem in dynamics learning is slightly different from the distributional shift problems in traditional deep learning settings, because distributional shift here usually refers to the distribution of the value on the data. But here, when you look at the sine curve, the distribution of the sine curves in terms of value are actually quite similar. So there is not much shift in terms of the data itself, but in this case, it's rather the underlying dynamics that governs the data that is changing from training to testing. And this is a slightly different scenario of distributional shift, and that's posed significant challenges to existing deep learning models. So our idea to address this problem comes from physics, and we use this idea of symmetry to alleviate the problem of distributional shift and improve generalization of deep dynamics models. Because the high-level idea is that we think, even though the dynamics have changed from training to testing, while we're working with physical systems, the laws of physics do not change. And because of that, if we can build physical laws into deep learning models, then we can automatically guarantee the models to generalize to unseen dynamics and stay and become robust to this kind of distributional shift. So there's intimate relationship between the concept of symmetry and conservation laws given by the famous physicist Noether. So Noether's theorem says that for every symmetry, there is a corresponding conservation law. For instance, translation symmetry will correspond to conservation of momentum, and time invariant symmetry will correspond to conservation of energy. So we want to build symmetry as a type of inductive biases into deep learning models such that it can help us improve the generalization of deep dynamics models to unseen scenario, unseen dynamics, reduce the sample complexity of learning, and increase our trust in AI. So that's a high-level idea of the talk. And that's before I talk about the technical details, and I want to just brush up on our knowledge on group theory and symmetry, which is the mathematical foundation of this talk. So this probably we learn from basically like grad school, like mathematics, where we have a concept of group. Right? A group is a set G with a composition map to itself. So G outer product G to itself. And identity is an element in this group. For every element G, there is an inverse element G inverse that also belongs to this group. So if we are familiar with groups, then we have probably heard about the special orthogonal group in 2 dimensions, an SL2 group representing 2D rotation. So we know that non-rotating is identity in this group transformation in this group. And then when we rotate this object by 60 degrees, there is a inverse group element, which is rotating this rotating this object counterclockwise by 60 degrees. So for every element G, there is a inverse element G inverse. With the definition of group, we can describe what we mean by symmetry in a more precise language. So symmetry is basically summarized in these 2 types of concepts. One is called invariance. The other one is called equivariance. So we're looking at a function f, and then given the particular group G, we can define the concept of invariance as follows, which means when we apply a group transformation to the input x, the output of this function does not change. In other words, f of g of x equals f of x. So if a function satisfies this condition under the group G, then we say this function is invariant, G invariant. The definition of equivariance is a more general notion of invariance. So in this case, when we consider a function f and the group transformation G, when we apply this transformation to the input of the function, then this transformation will automatically apply to the output of this function. If a function satisfies this condition, we say that the function is G equivariant. It's easy to see that when we pick the group to be the identity group on the right-hand side of this equation, then equivariance will reduce to invariance. So that's why I said equivariance is a more general notion of invariance. To give an example, let's consider the function of scaling. So f of x of v is a function on the velocity, 2D velocity field, and this function will stretch the velocity field by 2 in terms of magnitude. Let's consider the group as a 2D rotation group. We can represent this rotation group rho is the representation. So it's a matrix representation of the group element. So for the rotation group in 2D, we can represent it as a 2x2 matrix. So consists of cosine and sine functions. If a function f is G equivariant, then when we apply these functions of scaling to this velocity field first, and then rotate the velocity field by 45 degrees, so that's basically f of x and then g of f of x. And this is the same thing as we first rotate the velocity field by 45 degrees, and then scale the velocity field by 2. So this route represents f of g of x. So if f of g of x equals g of f of x, meaning going through the top right route is the same as going to the bottom left route, then this function f is said to be equivariant with respect to this group transformation. Any questions?
So F maps the group to the group. F maps the group to the group. What is the domain and the range of F?
F is a velocity field. It's from the field to the field.
No, I mean, in the equivariant definition, you're composing X with a group, and then you're composing the group with F of X. So F maps elements of the group to elements of the group.
Well, here G is an element of the group, right? And it's a group transformation. So F can just be, you know, this F lives in R2 essentially, right? It's a two-dimensional field.
So you have to define the action of the group then on two-dimensional vectors or something.
That's right. It's the action of the group on a two-dimensional velocity field, exactly. Okay, so in this talk is about deep learning, right? And after we define the idea of symmetry, and we need to define what we mean by symmetry-aware deep neural networks. And that's a study of equivariant neural networks. So we have a neural network that can approximate any function. So we know that a neural network is a universal functional approximator. So if we learn this function, we need it to be equivariant with respect to certain group. So we can write a function f as a sequence of functional compositions, and each layer is a function. And then a deep neural network or feed-forward neural network will compose each layer together and map the input features to the output features. So we want this function f, or neural network function f, to be G equivariant. And then in essence, we want every layer in this neural network to be equivariant. So in our paper, we show that if the maps between the layers are equivariant, then the entire network is equivariant. This is by the definition of equivariance, and we can show that through functional composition. So we know that in the input and output representation, all the input and output features are not up to our choice, and they're basically designed by the prediction tasks. So in image, for example, image classification, then the input representation is the pixels, and output representation are different classes of the image. But what we can do is intermediate representations, and these intermediate features or hidden representations can be designed in such a way that the maps are equivariant. So we show that in this paper that even adding skip connections does not change the equivariance of this function with respect to linear actions. So that's a high-level definition of equivariant networks. In practice, the way we can implement equivariant networks is actually through weight sharing. And this is an idea that is quite classical in deep learning community. And if we're familiar with how CNNs are designed, a convolutional neural network are designed, then we will understand how weight sharing can lead to symmetry or equivariant networks. Because we know that CNNs are translation invariant, meaning that it will extract features that are not changing along the translation direction. So in this case, the symmetry group G is a translation group that translates a pixel from the top left corner to the bottom right corner. The way CNNs achieve symmetry is through weight sharing, meaning that the weights, this is the weights in the CNN, and then the weights in this orange block on the top and the weights in the orange block on the bottom, they're exactly the same. So these two blocks in orange have the shared weights, and the weights within the orange blocks are freely trainable. So you can also think of this as, you know, a block diagonal matrix in the weight matrix of CNN. So typically when we talk about CNN, we will think of this like the filter, where we move the filters along different direction on the image, but then the weights in the filter are freely trainable, and the weights across different filters are shared. So by this kind of design, CNNs are naturally translation invariant. However, this is only for translation groups. For other general groups, there is this recipe given by Weiler and Sesta in 2019, which defines the general notion of group equivariance for any convolutional layers. Essentially, the kernel in this convolutional layer needs to satisfy a condition known as group invariance under conjugation. So, which means when we apply a group representation on the right-hand side of the kernel, and then multiply by the same group representation inverse to this kernel, then the kernel's outcome value stays unchanged. So if a kernel satisfies this kind of condition, then we say this convolutional layer is de-equivariant. So the kernel has the weights that are operating on local patches of the input. So the only thing we need to do is to figure out the correct type of input and output representation for the corresponding group, and that will basically become the key idea of our paper. So in this paper, we try to design surrogate models to speed up the simulation of turbulence. There's actually a lot of work recently about building deep surrogate models to predict the complex dynamics of turbulence, because turbulence simulation is very computational challenging. And deep learning model bypasses the numerical indication scheme and direct output the velocity field in the future. So that has seen a lot of success recently in engineering community for predicting or accelerating the turbulence flow dynamics. However, a lot of the existing work only design deep learning models for particular boundary condition and initial condition of the turbulence. And oftentimes when we train a model on the one type of fluids, they fail to generalize for different type of fluids under slightly changes of initial and boundary conditions. So we try to solve this problem through the idea of symmetry, and this paper was published in iClear this year, led by my PhD student and our postdoc. In this paper, we designed 7 different symmetries for differential systems, but I'll give you just one example of symmetry in terms of scaling. So we know that turbulence have a self-similarity, or also known as scale symmetry. So if we're looking at a turbulence like this, right, when we pour milk into coffee and we see small turbulence on the surface of the coffee, it has some similar behavior as this kind of large-scale turbulence in climate sense, where we're looking at the cloud turbulence for hurricanes or the ocean currents in the ocean. So we know that standard convolution shares weights across input by translation kernels across input, and then standard convolution is only translation invariant, and then they're not scaling equivariants. So in this paper, we designed a specialized scale equivariant kernel. And the key idea is that we actually have to translate and scale the kernel across the different input. Okay, so we actually studied the 2 types of systems in this paper. One is the heat equation governed by the sum of 2-dimensional, 2D, 2 second-order equations. And then we know that turbulence is actually governed by Navier-Stokes equations shown in this picture. And in fact, we actually don't need to know the physical equations of this dynamics. We only need to define what we mean by symmetry when we consider this type of physical systems. So we define the symmetry of a differential system as follows. Essentially, a differential equation, D, can be written as some composition of differential operators, P1 and PR, where P1 can represent the first order of differential operators such as velocity, and PR can represent first order differential operator to the velocity field. If we say that the phi is the solution of the differential system, and then when we transform the input of this solution, the solution is still a solution to the differential equation. In other words, g of phi, if phi is the solution of the differential equation D, and g of phi is also a solution to this differential equation g of phi, then we say that the differential system has the corresponding symmetry with respect to the group G. So by this definition, we can derive different type of symmetries of the 2 equations that I showed you earlier. This corner shows the heat equation, right? And then this column shows the Navier-Stokes equation. Basically this type of symmetry can be directly derived from the mathematical definition of symmetries for differential system. And I want you to pay attention to this particular scaling law that I'm going to talk about in this talk, where scaling of the Navier-Stokes equation has some interesting behavior. It means that when we scale the space by lambda, the time actually needs to scale by lambda square. So there is this kind of half space quarter time law for Navier-Stokes scaling for turbulence. And lambda here is the scaling coefficient. So it basically governs the scale. It just quantifies the scale of different type of turbulence. As mentioned before, we wanted to design convolutional networks that are scale equivariant. So we need to translate and scale the kernel of the corresponding convolutional neural networks. So given the velocity field, in this case, right, we basically upscale the velocity field by different factor lambda. And then we will design the corresponding convolutional filter to scan through this velocity field and extract features. So we need to enforce that the filters across different scales share the same weights. So that's actually quite similar to the traditional CNN architecture design. So the weights along these different blue patches are all shared across scales, but then the weights inside of this kernel are freely trainable. So by this way, we can achieve the idea of scale equivariant. And because of the scaling laws of turbulence, we have to apply this kind of scaling operator on the outside of the kernel outputs. So we have the kernel K operating on the velocity field. And when we sum over different scales, where lambda representing the scaling factor, so we need to sum over the features extracted by different scales, and then rescale the velocity field by this T of lambda, which is a scaling operator coming from the scaling laws of Navier-Stokes equations. And in this way, we can guarantee that this kernel learned from specialized convolutional neural networks, the features are equivariant under scaling for Navier-Stokes equations or turbulence. So we showed this example for a real-world ocean current forecasting data set. This is an NOAA reanalysis data set, which basically contains the velocity field of the ocean. What we want to do is to build surrogate models to predict the ocean into the future as a forecasting task. So the model will take the past velocity states as the input and then generate the predictions for the future states of the ocean. We're looking at basically the comparison between the non-equivariant models, ResNet, and the equivariant counterpart of this model, the scale equivariant ResNet. This plot shows the forecasting RMSE in terms of root mean square error. And then this picture, this x-axis is the upscaling factor 1 over lambda, where lambda is a scaling coefficient. So the experiment works as, we train our model in a particular scale of the turbulence. And then we will upscale the test data by different factors, mimicking the behavior of generalization. So it's creating an artificial test scenarios for generalization, where the model needs to know how the data is different from training to testing and be able to adapt to different type of scales in ocean current. So it's actually not surprising that the equivariant model can automatically detect the changes in the scale and being able to generate the corresponding forecast with robust performance, whereas non-equivariant model will have exploding error because the model is not equivariant and suffers from the distributional shift problem I mentioned in the beginning of the talk. And then the right plot is actually a different metric. It's very important in physical system modeling called energy spectrum error. So this basically quantifies the energy cascade in the turbulence. It's a physics-based metric. And again, we can see that the predictions of our model in terms of the error is very robust when we upscale the data by different factors, whereas a non-equivariant model does not have this robust performance. This result shows that by incorporating symmetry as an inductive bias, we not only can obtain very robust performance in terms of mean square error, but we can also ensure the physical consistency of the predictions when we change the distribution from training to testing by different scaling. There's a question, is it only due to the physics and model-based analysis that you know all the symmetry? What if you face a real black box? Where do you not know the symmetry in advance? That's a wonderful question. Thank you, Florian. So that's actually a point naturally lead to my second part of the talk, which means that if we don't actually know the symmetry of the system, how can we design neural networks that can understand the properties in the physical system and being able to generalize, right? And that's this new paper that we wrote on meta-learning dynamics forecasting to forecast the ocean currents again, but without relying on the explicit knowledge of symmetries for differential equations. And again, this is led by my PhD student, wonderful PhD student, Ray Wang, and postdoc, Robin Waters. And this is a very recent paper. You can find it on arXiv. So in this paper, what we wanted to do is generalization, right? But in the previous talk, I only talk about generalization within a certain group transformation. In this case, we're looking at a much more general scenario where we don't really know the symmetry groups. So in the setup, we have the turbulence in the past as initial conditions, and we feed this as an input to the neural network. We want the neural network to be able to forecast into the future. So you can see that when we train our model with a particular type of turbulence, and this turbulence is very smooth, it has very mild behavior, we want the model to be able to generalize, that's in this question mark, to a much more turbulent regime. So in this case, in the testing, we will give the model very different type of initial conditions, as then shown in the bottom plot, and we hold the model to be able to predict the corresponding velocity field in the future. So this is our goal. We want to build deep learning surrogate models to generalize flows with very different buoyant forces. So buoyant force is this external force that drives the flow. And if a higher buoyance factor, it will lead to much more turbulent behavior of the flow. And the key idea is that, again, symmetry, right? We think that similar dynamical systems will share some time invariant hidden features. And now the key idea here is that we're not going to work with symmetry in the observational space anymore because we don't really know the symmetry from this real world data. And they might not have the perfect symmetry, but instead we're going to work with the symmetry in the hidden space or in the latent features of the neural network. We hope the model can infer the hidden features from data, and therefore when we enforce the symmetry in the hidden features, the model will be able to judge and adapt to very different type of dynamics. And this is our final model architecture, and we call this dynamic adaptation network, or DyAd. So this model takes actually have two parts, right? So we will first identify each forecasting task by some parameters. And this parameter is governed different dynamics such as constants of motion, external forces, or boundary conditions. And we will give the model different type of data, so from different regimes, right? So each sequence represents a task, a forecasting task. This is turbulence for a particular buoyant force, and then this turbulence is a different type of buoyant force. So we put all these tasks together and train the model simultaneously. So this part uses multitask training. And then we use an encoder network, right, shown on the bottom, to infer the time invariant hidden features. So this encoder network achieves the symmetry through two aspects. One is through the design of the network. So that's the time shift invariant encoder network. And we can see that in each layer of this encoder network, the specific layers are chosen such that it stays time in shift invariant, because we think the buoyant force is not changing from the previous states to the next. So these should corresponding to the time shift invariant features, then the model needs to infer. And this architecture itself, by 3D and pooling operators composed together, achieves the time shift invariance. And on top of that, we also use optimization-based technique to modify the loss function for the encoder network. So we use this encoder network. It takes the path velocity field of the multiple turbulence, and then it will map into some hidden features Z of C, where C is a task parameter. So we think Z of C represents the task specific features, but we want this task specific hidden features to be time invariant. So what we did is that we will use this three-part loss function. where C hat is a prediction of this neural network from a fully connected layer. So C is a linear combination of the hidden feature that can be predicted. And we think that C is representing, the task-specific behavior. So in this case, C will just corresponding to different buoyant force. So we'll predict the C, right, using the ground truth C, where the ground truth C is just some surrogate computed from the input. So because the buoyant force will drive the velocity, so in this case, the C is computed as the average velocity of the field. And then we wanted to make sure that the predicted C, this inferred task, is close to what we think is the true task for different turbulence. And the second task, so this is a task parameter. And the second loss enforces time invariance, right? I and J are time indices. So we want two timestamps. It doesn't matter which timestamp, any pairs of the timestamps of the ZC to be exactly the same. So this is the loss function that enforces time shift invariant. And the third part is some sort of regularizer that avoids the pathological cases of ZC to be 0 everywhere. So by combining the architecture design and the loss function together, we can ensure that this encoder network can generate time shift invariant latent features, D of C. So we train this encoder first, right, to obtain the latent feature ZC, and then we will use the inferred latent feature ZC to adapt the forecasting network. So in this case, the forecasting network will be able to condition on whatever hidden features have been inferred for each different tasks and use this learned feature to adapt its prediction. You can use any forecasting network. In this case, we just use a ResNet and a UNet, but you can use, we also experimented with different state-of-the-art forecasting network or sequence models or predicting RNNs, any of the favorite model architecture in forecasting network, as long as it can use the hidden features inferred from the encoder network to adapt its behavior. And after that, during the adaptation phase, the model will be able to predict for turbulence with very different behavior. So adaptation actually uses two techniques. One is called adaptive instant normalization. This is inspired from the literature of neural style transfer, where we transfer the styles of different paintings from one artist to the other. In essence, we need to compute per channel mean and standard deviation. So Z is our inferred hidden features, and A and B are trainable weights. So this represents a linear transformation of the hidden feature. And it will generate the mean and standard deviation per instance and for per channel. And after that, we will normalize every training example by this mean and standard deviation. So mu of xi, where xi is every data point, and mu of xi is basically the per instance mean and per instance standard deviation. And then we need to normalize it by the channel mean and channel standard deviation. So this is adaptive instance normalization. The second technique is what we proposed as adaptive padding. And this is designed specifically for the boundary conditions of the turbulence. Adaptive padding essentially computes the boundary conditions. Use similar ideas of transforming the hidden features by some linear operation. So we will compute the boundary condition H as a linear transformation of this hidden feature Z, where A and B are trainable parameters, and H is an inferred or computed boundary condition. So what we do is that we will take this hidden feature Z, pass it into a fully connected network, which represent A and B, and then we will feed that into it to give us the hidden boundary condition. So we will basically pad this hidden boundary condition along the output of the X, which is our input features, and that will give the corresponding boundary condition outside of the spatial domain. So these two techniques combined enable the forecasting network to adapt to different tasks, different boundary conditions, different buoyant force according to the inferred task parameters. We showed in the paper that essentially this is a theory that generalized the classic theory, learning theory on Endo in 2005 on multitask learning. So essentially we showed that multitask training paradigm has better generalization in terms of learning each task independently, because one simple strategy is just to train a model for individual tasks specifically, and then just use a different model, hopefully to adapt to a new task. But we show that with multitask training, we can improve the generalization because we can allow the model to learn the similarities between different tasks and transfer knowledge across tasks. So the shared data will tighten the generalization bounds. In terms of prediction performance, so we looked at 3 different types of flow data. Turbulent flow is a synthetic turbulent flow data. Sea temperature and ocean currents are 2 real-world data sets. Sea surface temperature is a collection of, it's a scalar field recording the sea temperature across different locations. And then ocean current temperature is a reanalysis data set for NOAA. So we're looking at 2 different types of generalization scenarios. So one is about in terms of different initial conditions. So we call this test future. This means that when we train our model from different type of initial conditions along the time axis, we will test our model on a different type of initial condition into the future. So this is trying to test whether the model can generalize to unseen future and in terms of time, right? And the second type of generalization scenario is in terms of space. So we call this test domain. In essence, we train our model in some locations of the turbulence or on the sea temperature data set, we will select specific locations or geographic regions of the sea surface temperature and train our model. And then we'll test our model on the very different geographic regions of the Earth, hoping that the model can learn to generalize to unseen locations. So this is what we call test domain. So it will corresponding to different parameters, right? Because different locations on the Earth will have different type of behavior. And then for turbulence, it will correspond to different external forces. So we compared with a large set of baselines. So ResNet and ResNet-C. So these 2 baselines are just a specific modification of a non-equivariant or symmetry in kind of vanilla forecasting network. PredRNN is a state-of-art forecasting network without adaptation. So we included ResNet-C and UNet-C as suggested by one of our reviewers, because they feel that, well, since our model uses weak supervision, right, we use some computed velocity field as supervision of the specific task. So it might not be fair just to use a forecasting network, because these models might not have the same input information as this additional weak supervision, even though the weak supervision is only computed from data. So the model actually doesn't know what external force the data comes from. But in any case, we've included the C as additional input to this ResNet to give the exact same information for these baseline models. The only difference between our method and the existing baseline is that we kind of use this velocity, this supervision in a smart way, right? We will learn the hidden features and learn the hidden features to adapt to the prediction network. Then we compared with a bunch of different meta-learning methods. And these 3 methods are modular-based meta-learning methods. So you will use a different deep learning module to learn a specific task, and then combine the modules together using some weighted averaging or attention to learn the meta dynamics. And then MetaNet and MEMO are state-of-the-art. MEMO and model agnostic meta-learning methods. These 2 methods are state-of-the-art methods for meta-learning. We can see that for both the testing scenarios, for future and the domain, when we're looking at generalization, so this is a value in terms of RMSE, we can see that our model achieves the best results across all different tasks. It shows that the model can generalize for both scenarios across multiple data sets. And then for ocean currents, we also evaluated on the physical consistency that I showed before, and that's basically the energy spectrum error shown on the right-hand corner of this table. And again, we can see that the prediction error of our model achieves the best performance, not only in forecasting RMSE for future and the domain prediction, but also in terms of the ESE, the energy spectrum error. So let me show you the prediction of our model compared with the baseline. So this is showing the prediction of a model for a buoyant force at value of 9. So this represents a relatively smooth buoyant force. So target is a ground truth. DyAd is our model. Modular weight and resonance are two baselines. This is the mental learning baseline. It has the best performance in the previous table. So if you look at the actual prediction of the model, right, when we look at the behavior of turbulence, then our model can accurately mimic the rotating pattern of the turbulence and even capture the small dynamics. Whereas in contrast, the modular-based meta-learning network has some weird artifacts in this kind of zigzag patterns. And the ResNet can only learn the smooth behavior, the large-scale rotation, and it loses a lot of the small-scale behavior. A nice thing is that we can actually manipulate our model in the hidden space and enable our model to predict for buoyant forces of a completely different value. So this is looking at the buoyancy factor of 21, where the model has never seen it before in the training set. So when we look at the predictions of our model, right, for this much more turbulent forces, you can see that our model can generate accurate dynamics, can learn accurate dynamics and predict both the large scale and small scale dynamics, whereas the modular-based meta-learning has some really weird artifacts. And again, ResNet is learning quite smooth behavior, but it does not capture the small scale behavior dynamics. Okay, so to conclude, right, I talked about some ideas that our group has worked on to improve the generalization of learning deep dynamics, especially for complex nonlinear dynamics, for turbulence modeling and fluid flows. I talked about Equivariant Network, which is a set of tools that can encode symmetries in differential equation and through weight sharing to enable model generalized within a specific group transformation. And talked about dynamic adaptation network, which is working in the symmetry in the hidden space, so that the model doesn't have to know the symmetry with respect to certain differential equations, but can infer the specific tasks and being able to adapt to unseen scenario and unseen tasks. We're actually working on multiple angles of this method. We're very interested in developing new methods that can enable deep learning models to generalize to much more complex scenarios that can account for uncertainty with probabilistic modeling and can account for interactions in multi-agent behavior. We also have several papers on that, but I probably won't have time to talk about that today in detail. So you can check out the code and the data on my website or follow me on Twitter. And here are the funding agencies that support this work. Thank you.
Thank you very much, Rose, for the great presentation.